so it was really loud. Okay, today, thank you very much for accepting our invite. So today we have the pleasure of having Haizhao Yang. So Haizhao is an associate professor at the University of Maryland, College Park. So I enjoy his papers very much. He specializes in theoretical foundations of modern AI. So this range has a pretty broad range, of topics from approximation theory of neural networks, neural operators, some like learning theoretic results. There's some optimization results. Honestly, you have like a pretty broad range of very interesting things. And today he'll be speaking about one thing that I think is, in the early stages in the literature, so it's quite interesting. So they're like, yes, exactly, guarantees for neural operators. And yeah, the specific talk is going to be error analysis of neural operators for forward and inverse problems. So there's many people and some people in the audience I know who are not only from McMaster, some neural operator specialist just came in. So I don't know if you're interested in this. So after you, floor is all yours. Yeah.
Thank you very much for the invitation. It's my great pleasure to speak here to introduce some recent results on the error analysis of neural operator for learning solution operator for solving forward and inverse PDE problems. The operator learning problem is to learn some operator between function spaces. This function space could be Banach space, and the operators typically are assumed to be Lipschitz contains operators. Operator learning has broad applications in scientific computing. For example, in reduced order modeling, we want to learn operators in low-dimensional space so that we can make fast prediction. In solving parametric PDEs, we want to learn the operator from the parametric function of the PDE to the solution of the PDE, so that we can efficiently solve parametric PDEs. And in inverse problem, we can learn the operator from the data measurement to the reconstructed images. There are many similar applications where we want to learn an operator from a certain function space to another function space. If we consider discretization, then we are learning some discrete operator mapping from high-dimensional vector space to another high-dimensional vector space. So this learning problem is typically high-dimensional or even infinite-dimensional. This is a supervised learning problem where we assume that we have some data samples like functions pairs ui, vi from the space x and y. And the vi function is generated by the ui function with the unknown operator with some possible noise. Our goal in this supervised learning problem is to learn the unknown operator from the samples. Typically, we try to use neural network as a parameterization tool to parameterize the unknown operator. And we try to solve some optimization problem to get the best possible parameter theta star of the neural network, such that the learned neural network can approximate the target operator very well. So this is the in general operator, supervised operator learning setting. For example, I will give you some example of basic operator learning neural network to help you to understand what's going on in supervised operator learning. Suppose we have a function space X with function U and function space Y with tag the output function V. We want to learn the mapping from U to V. Because the functions are from infinite dimensional space, and it's impossible to do computation on infinite dimensional function space. So we have to do discretization. And this discretization can be considered as decoder, decoding a function U to a finite dimensional vector in RDX. And we consider the decoder as some scheme that decode a finite dimensional vector in RDY back to the output function V that we want to generate. And between the RDX and RDY, we try to use a neural network to learn the mapping. And in this learning scheme, there are many different kinds of encoder and decoder. For example, in the PCA net, we can use PCA to generate the basis function in a data-driven way. With this basis function, we can discretize a target function U to coefficients corresponding to this basis function to generate a vector in RDX. And given coefficients, we can use basis function to generate a target function V using the coefficient with as the linear combination coefficient with the given basis function from PCA. And in operator in deep net, then we could use sampling as the encoder. Given a function, we just sample the function at a certain grid point to generate a vector representing the given function. And in deep net, the decoder it's a procedure that learns neural network as basis function. With this basis function, given the coefficient in RDY, you can use linear combination of this neural network-based basis function to reconstruct a target function V. So there are many different ways to do this encoder-decoder structure. And in between, we have a neural network of a fixed size to learn the mapping from RDX to RDY. So this is the practice in scientific computing to learn an operator to solve PDE or inverse problem. In today's talk, we're talking about error analysis for this kind of supervised learning scheme. Our goal is to establish some a priori error analysis for learning these operators. This operator may possibly be nonlinear operators because the learning problem is high dimensional or even infinite dimensional. So we wonder whether we have the curse dimensionality in this learning problem. Our message is that in general, we will have the curse dimensionality because there is no free lunch. But in many applications of PDE problem, we realize that there is some special structure in solution operators for PDEs. And hence, we can lengthen the curse dimensionality. And we will give you some example to understand this point. As you can see in the basic computation framework, we have encoder, decoder, and fixed size neural network in the middle. The encoder and decoder are some standard tool like sampling, basis function expansion. So the error analysis have been well established. So we will only focus on the learning error analysis for the middle part, for the neural network part. And hence, when we try to use this basic structure to learn the target operator, we assume that the encoder and decoder are given through some pre-training to get some encoder-decoder part using the first n samples, and we are not going to analyze the error for this pre-training. And we assume that we use the second half of the samples to learn the middle part, the neural network, and try to analyze the error for this learning task. And hence, more specifically, we assume that we try to use a neural network gamma theta to learn the middle part. Together with the given encoder and decoder, the composition can learn the target operator. And hence, we try to propose, well, typically, the empirical risk minimization is proposed as follows. For the given function pairs, UI and VI, we try to learn a good neural network such that the composition here can generate an approximation to VI from UI. And if this approximation is good for all these n samples in the training, then the corresponding neural network gamma theta is believed to be a good neural network such that the composition here can approximate the target operator psi very well. So we are concerned with the approximation and generalization error analysis for this scheme. So we assume that we are able to identify the global minimizer of this empirical loss minimization problem. Of course, how to guarantee that we can get the global optimization is a very challenging topic and very interesting topic. But this is still an open problem. So here, we after assuming that we can get the global minimizer denoted as theta star, we wonder how good the global minimizer is. So we will substitute this global minimizer into the neural network to get an operator and try to use the population risk defined here to quantify the test error for this global minimizer. And if the test error here is very small, then we believe that the learned neural network is a good solution of the supervised operator learning problem. In the population risk, we not just consider the given samples. We will consider all the possible distribution of the functions u and v. And hence, we have the expectation over some probability distribution of functions to define the population risk. If we can learn a neural network size theta, defined here with the neural network gamma theta, if this operator can approximate target operator very well for all the possible functions following the distribution. In other words, the population risk is very small, then we believe that we have solved the supervised operator learning problem very well. So today's analysis goal is to try to analyze the population risk given the global minimizer of the empirical risk. If we substitute this global minimizer theta star into the population risk, then we try to analyze how large this population risk is when we consider different kinds of factors in the learning precision. For example, we consider how large the neural network is in terms of the width and depth so that we can understand how to choose the neural network size in practice to reduce the population risk. And for another example, we also want to consider the problem like how many samples are enough to guarantee that we can get a small population risk. And especially, we talk about the curse dimensionality. We wonder whether the number of parameters or number of samples would be exponentially large in terms of the dimension of the learning problem. If we do have the curse dimensionality and we in theory, then we cannot afford to solve this supervised operator learning problem well. If we do not have the curse dimensionality, we can theoretically say that in practice, we can probably learn the operator well with a small number of samples and parameters that are affordable.
That's one question, if you don't mind. So here, what is meant by dimension? Is it the dimension of the, like, if the Banach spaces are like, are we thinking of them as, say, like, some sublove spaces and there's a physical domain? Or is it something like some dimension of, like, gamma, like, of the supports of gamma? Like, yeah, just to know what is meant by dimension here.
Mm-hmm. This is a very good question. So we have two kinds of dimension here.
Mm-hmm.
We have a Banach space is a function space, and these functions are defined on a domain, omega. And we have the dimension of the domain denoted as capital D. And the Banach space itself is an infinite dimensional function space. So we have two kinds of dimension here. And typically in operator learning, we assume that this capital D is small, is order 1. And we concern, if we do discretization to the Banach space, then we can get some linear space with finite many dimension. And we consider this dimension could be possibly high. And we talk about the cross-dimensionality of this high dimension.
Good, thanks.
Yeah, the reason why operator learning may not be able to solve problem for this large D is that if we have large D, then the discretization of the function space may lead to some vector that is exponentially in capital D large. And we may have the cross-dimensionality in the discretization of the Banach space, and hence the computation is not affordable.
That makes sense. Thanks.
Okay, so now let's go back to our problem statement. And our goal is to analyze the population risk here. And we can divide the population risk into two parts using the typical bias and variance decomposition. And we can see that in the bias part, we just artificially create the blue term, and hence we can decompose RD into T1 and T2. And the T1 term, it's called bias term, and in fact, it's related to new level approximation, because the problem is to try to see whether we can have a new level such that with this composition, it can approximate the target operator psi very well for these n samples. So this is essentially new level approximation problem. And in the T2 term, which is called a variance term, this is also called generalization error analysis, meaning that if we solve minimization problem to get gamma theta star, how well this gamma theta star can generalize well from n sample to all the possible function distribution. Because the difference here, it's the difference between the approximation from this n sample to all the possible function distribution. This is called generalization error analysis. For the first one, T1 term, if we can reformulate this T1 term. Originally, this T1 term is defined for the norm in the Banach space Y. And we can reformulate this T1 term by considering that we have the decoder as a Lipschitz continuous operator with Lipschitz continuity constant Ly. So if we pull this dy out of this norm and expectation, then we can result in this Ly square. And the norm in the Banach space is reformulated into the norm in the L2 space, because this is the vector space RDY. Because given the function u, you have encoder to make it RDX, a vector in RDX. After fixed size neural network, you can generate a vector in RDY. So now the error is in terms of the L2 norm of RDY. And hence, if you focus on the error analysis here, you see that this is a standard DNN approximation problem, where you have a neural network in red together with the encoder decoder, mapping a vector EXU in RDX to a target vector gamma of EXU in RDY. So this is a neural network approximation problem from RDX to RDY. And we can use standard neural network approximation theory to get the error analysis here. Especially, our goal is to understand the error in terms of network width and depth, so that we can have a good guidance on the choice of deep and depth width and depth in practical computation. And we also wonder whether the curse dimensionality exists in this neural network approximation. In other words, if we want to try to achieve epsilon accuracy, whether the number of parameter will scale like exponential indeed large or not. There has been a lot of literature in studying the deep neural network approximation. We're going to have a brief review of the result to understand the key question that we are concerned with. For example, we have developed some neural network approximation theory for red-rule neural network with width n and depth L. We show a nearly tight approximation rate, which is of the order here, and omega f is the modular continuity. If you're not familiar with modular continuity, we can reduce the target function to Lipschitz continuum function, and hence the modular continuity function will be reduced to a linear function. And we can essentially ignore this modular continuity here. And you see that the error scaling is essentially n to minus 2 over d times L to minus 2 over d. And we can improve the approximation rate with smoothness, but the smoothness can only improve approximation rate, but it cannot help to avoid curse dimensionality in this error rate. We have the curse dimensionality because of the 1 over d term here, and we can easily prove that because of the 1 over d term, the number parameter required to achieve epsilon accuracy is exponentially large in 1 over epsilon. So this is the bad news. We do have the curse dimensionality if we have red-rule neural network to approximate continuum function and even CS function, smooth function. So we wonder whether we can have some better neural network so that we can possibly avoid curse dimensionality, because originally in our goal in the operator learning, we try to understand whether we could avoid curse dimensionality in the learning problem. Okay, so if we do have curse dimensionality in the neural network approximation, this is bad news. That means that we cannot avoid curse dimensionality in the operator learning problem. So we further investigate the possibility to see whether we can avoid curse dimensionality. And then more recently, we discover a very powerful activation function, which is called the elementary universal activation function, which is visualized in blue here. It is a continuous activation function. And we prove that using this continuous activation function, we can avoid the curse dimensionality in terms of number of parameters in neural network approximation. In particular, if we have a target function as a continuous function defined on the unit hypercube with d dimension, we prove that for any arbitrary small accuracy epsilon, we have a neural network of size order d squared and depth order 1, such that this neural network can approximate the target function uniformly well on the domain of the function, controlled with epsilon accuracy. The reason why we claim that there is no curse dimensionality is that the number parameter required is only polynomial indeed. It's square, d squared, orders d squared. More surprisingly, even if we have smaller and smaller learning target error, the number of parameters does not change. It's independent of epsilon. So this is a very strong approximation result. However, when we try to use this approximation result to analyze operator learning error, we discover that it's difficult to balance approximation and generalization so that we can get a very good error bound for the learning problem. The main reason is that if the approximation power is too good, then the generalization error could be very bad. It's particularly for this neural network, the pseudo dimension is infinite, meaning that the neural network can overfit arbitrary large number of data, and hence it's difficult to control the generalization error. And hence, this is a story to tell us that it's good to have good approximation capacity, but if it is too large, then it may not be very practical in machine learning. So we will go back to revisit the red-rule neural network approximation theory and apply this theory in our operator learning analysis. And we hope to use some other structure to possibly avoid curse dimensionality. And this idea will be discussed later. So now we have finished the discussion about the T1 term in the full error analysis of the operator learning error. We're going to talk about the T2 term. The T2 term is a generalization error analysis, and we could apply some established statistical machine learning technique together with some modification and generalization to get the error bound for T2. The roadmap for controlling T2 is given as follows. First, we are going to use the covering number of neural network of a fixed size to bound the T2 term. And then we're going to use the pseudo dimension of the neural network to provide a bound of the covering number. Finally, the pseudo dimension of the neural network is related to the size of the neural network, so that we can get some error term in terms of the size of the neural network and number of samples to bound the T2 term to finish our proof. By reformulating T2 term, we can prove that it can be bounded by a term like this, where n is the delta covering number of neural network with 2n samples. And this covering number can be further bounded using pseudo dimension of the neural network, using the famous theorem by Antoni and Bartlett 25 years ago. And then we are going to use the another theorem by Peter Bartlett, trying to use the network size to bound the pseudo dimension of the neural network, where the network size notations are L layers and U parameters, so that we can use number parameter and the size of neural network to finally bound the T2 term, and also the number of samples. Combining all these partial results together, we can get our full error analysis. So
Can I ask one small question, if you don't mind?
Yes.
I can go back at 2 slides, bro. Sorry, 3 slides. Yes. Yeah. Just maybe because it's the morning for me, so I need more coffees and something. But just want to know why do we only look at the covering number of this class of null networks and not the covering number of the concept class with C can live inside? Because maybe the operator C is like only Lipschitz or something, and this covering number might be much bigger.
Yeah, right.
Just as an idea, but maybe I need more coffee, so feel free to delete the question.
Are you asking the question?
Oh yeah. Yeah,
Could,
just yeah. Just if the answer is easy, if not, it's okay. Yeah, yeah. So the question is just simply like yeah. I guess my question just to reiterate is mostly just that why do we only look at the covering number of the neural network class and not also the covering number of the class where the target function can live?
where the target function converge.
I can live like because the target function C, I guess it's just some Lipschitz function. So it's yeah. So it's covering number is something like also 1/epsilon to the d, I guess. I mean the covering number of the one bounded Lipschitz functions on d-dimensional space.
Because we are trying to oh, you're asking why we are not using covering number of these C functions.
Oh yeah, both together. Yeah. But
because we try to understand the complexity of, I mean, the richness of this neural network to learn the target function. That's why we use the covering number to measure the richness of this neural network function class instead of the target function class.
Okay, fair enough. Thanks.
Yeah, this is a very good question.
Thanks.
So if we combine all the partial results together, we can get our final error analysis. This is a kind of informal theorem. As we claim that we want to study the curse dimensionality and also the arrangement of the network size, like the width and depth, to achieve some good guidance in practice. So we have in all the partial analysis, we have some error term in terms of the size of the neural network, like the width and depth, and also in terms of number sample of the training. And we try to optimize the final learning error by choosing the optimal neural network size, like width and depth, to minimize the final learning error. So we concluded that if we given the number of sample n, if we choose the neural network depth L and neural network width n, such that they satisfy the following criteria. Like given n, you can essentially compute a number here because dx, dy are given. And as long as you can choose L tilde and P tilde satisfying this equation, then this L tilde and P tilde can give us the best possible neural network depth and width to minimize the final learning error. And if you do choose this depth and width, then the final learning error has the following scaling in terms of the number of sample, lowercase n, where we have three terms. The second term and the third term are related to how good the encoder and decoders are for the x function space and the y function space. Because we're not concerned about this learning problem, so we assume that the encoder and decoder are well chosen so that these errors are small. We just focus on the first term, and this first term is the error corresponding to the neural network learning for mapping from high dimensional space to another high dimensional space. And we can see we do have the curse dimensionality in this learning error because dx could be very large. Dx is the dimension of the after discretization of the function space, and hence dx could be very large. If dx is very large, then the number sample, according to the error analysis here, should scale exponentially large in dx to make the final error meaningful. And hence, we do have the curse dimensionality in this learning result. So as I said, we try to understand how to lengthen the curve dimensionality. So right now we have two difficulties that we cannot solve. The first one is the neural network approximation difficulty, where we do have a curve dimensionality if we have rule neural network. And secondly, in terms of the number sample, we also have the curve dimensionality. So what other idea can we explore to possibly lengthen the curve dimensionality? The idea is that, well, in general, because there is no free lunch, it's difficult to believe that we can avoid curve dimensionality for general operator learning. But if we do have some structure in the learning target, then we may possibly lengthen the curve dimensionality. We have two ideas to explore this low complexity or low dimensional structure. The first idea is that if we could assume that after encoding, all the functions in the finite dimensional representation lie on a low dimensional manifold with a dimension d0 much smaller than dx, then we could improve our result to lengthen the curve dimensionality. We have a more recent paper on operator learning theory with a cleaner result. I mean, the notation and the error bound is simpler to understand. And we can prove that with this assumption, the final learning error has a scaling like this in terms of number of sample n. And we don't have a curve dimensionality in capital Dx anymore because we have D0 here, which is small. So this is first idea. And the second idea is to explore some low complexity structure. The low complexity structure, more specifically, is a structure that if we have a target operator, that is the composition of essentially linear transformation and some nonlinear entry-wise function evaluation, then this composition has low complexity. Intuitively, we can understand this. This linear transform and nonlinear entry-wise evaluation and their composition is very similar to a neural network structure. So if our target function has this structure and we use neural network to learn that, that means that our hypothesis space is very similar to the target function space. And hence, it's very natural to expect that the learning task is simple, and hence we can get nice error bound to possibly avoid curve dimensionality. And mathematically speaking, the notation to define this composition of some linear transformation and some nonlinear entry-wise function evaluation it seems complicated. But I can give you some simple example to see that actually we have many nice PD operators satisfying this low complexity assumption. For example, if we just consider there's no function composition. We only have one linear transformation and another layer of entry-wise nonlinear function evaluation to create a map. Then this mapping is very simple. It's simpler to understand. And as an even much simpler example, we don't have this nonlinearity G. We just have a linear transformation. Then it is a very special and easy to understand low complexity learning target. If we want to learn the linear transformation, of course, it's simple. So if we do have this low complexity assumption, we can improve our error bound to a new error bound, Well, we have D0 here to quantify the complexity of this low complexity structure, where D0 it's essentially the size of the linear transformation. And we can reduce our error bound to a nicer error bound that has no Kurt's dimensionality because we only have D0 and it's a small number. So this low complexity assumption is very useful in the study of learning PD solution operator. I will give you some simple example. For example, if we want to solve partial equation repeatedly with many different kinds of right-hand side, then in this application, we could potentially learn the solution operator such that given the right-hand side as the input of the solution operator, we can generate the solution U as the output of the solution operator. It is well studied PD theory to show that this solution operator can be given by the Green's function and the integral transformation. And given the Green's function and the integral transformation, we just do the integration, we can get the solution given the right-hand side function f. We can show that this transformation from f to u, it's a linear transformation, and hence it's a low complexity learning target operator. So we can apply the theorem here with this low complexity assumption to lengthen the Kurt's dimensionality. The second example is the solution operator for solving parabolic equation. For example, we have an equation here. We try to learn the solution operator mapping from G to the solution U at a later time step T. So it is also well studied, and we can show that the solution at the later time step T is given by the convolution of a function psi with the right-hand side, the initial condition G. And hence, this is also a linear transformation in terms of G, and hence it's low complexity. And applying the previous theorem, we can show that the Kurt's dimensionality for learning this solution operator is lengthened. The third example, it's the solution operator for solving transport equation. Very similarly, we can show that if we want to learn the solution at later time step T, we can prove that this solution is given by a linear transformation of the initial condition U0. This linear transformation is given explicitly with the formula here, and hence the Kurt's dimensionality for learning this solution operator is lessened. And in all these examples, there are some simple examples where the target operator is a linear operator, and hence it's simple to learn. You may wonder, what if we have some nonlinear operator? Can we still have some low complexity so that we can avoid or lessen the Kurt's dimensionality? So the final example is an example for the solution operator of Burger's equation. Given the initial condition U0, we try to solve for the solution at a later time step T. So we want to learn the solution operator mapping from U0 to U capital T. And this mapping is nonlinear. Fortunately, we can apply the so-called cohort transformation to linearize this learning problem with simple nonlinearity. And we can actually show that this cohort transformation is indeed a composition of linear transformation, nonlinear evaluation, linear transformation, and nonlinear evaluation, and so on. So this is exactly a particular example of low complexity operator. So what is the cohort transformation? we introduce a new variable, new function v, and the relation between u and v is given by the equation here. So given the initial condition u0, we have a linear transformation mapping from u0 to v0. This linear transformation is given by, well, this is not a linear transformation. We have a linear transformation given by this integral transformation from u0 to the to this equation. And then we have nonlinear function evaluation, exp, evaluate on this output function of the integral transformation. And hence, the mapping from u0 to v0, it's a composition of a linear transformation and nonlinear function evaluation, which is low complexity. And given this v0, we want to solve the linear equation to get v at a later time step capital T. And the solution operator for solving this linear PDE is linear, and hence is low complexity. After getting the v function at later time step t, we can get back the u function at later time step t using the equation here. And this mapping from v to u, it's also low complexity because computing the derivative vx, it's a linear operator. And generating the ratio here between vx and v, it's a low complexity function. It's a nonlinear function entry-wise evaluated on vx and v. And hence, it's a low complexity function. So from this discussion, you can see that the mapping from u0 to u at a later time step capital T, it's a sequence of composition of linear transformation and nonlinear function evaluation, and hence it's low complexity mapping. And we can summarize our discussion using this following slide. Given u0, we generate v0 with low complexity transformation. And given this v0, we can solve the linear equation using integral transformation, which is the linear transformation. Given v and vx, we have nonlinear function evaluation to generate u at the later time step t. And hence, the mapping from u0 all the way to u capital uxt has low complexity. And applying our analysis previously, we can show that this operator learning problem is the curse dimensionality of this operator learning problem is lessened. So these are all the stories that I would like to share. And if you are interested in the theory and even some computational routine for solving forward and inverse PDE, you could read our paper published on JMLR for numerical implementation of discretization invariant learning. And you could read our paper for solving for operator learning in general in this JMLR paper. And for learning PDE forward problems in this TMLR paper. And more recently for learning some operator for inverse problem in our preprint. I'm sorry that I don't have time to talk about the example for learning the inverse operator problem here, but the analysis is similar. But we need to have some new technique to deal with the ill-posedness for solving inverse problem, and we try to use regularization technique to define an appropriate operator learning to learn, and apply our analysis to get error bound for this operator learning. And I would like to thank my funding agencies for the support of my research. That's all. Thank you.
Well, thank you very much for the nice talk. Let me just, there we go, the clapping emoji. Does anyone else, I have maybe one question, because I mean, I tried to ask questions during, does anyone in the audience have any questions? Oh, okay, so there's a question from one person in the audience. So Lucas says, yeah, many nonlinear operators arising in practice are non-Lipschitz. Have you considered more general classes of operators? Yeah.
We have been thinking about this question, but our direction is to have stronger assumption. For example, some smoothness in this operator learning in the target operator so that we can improve our error bound. And your question propose a more challenging setting where we have non-Lipschitz contains operator. So this analysis is very challenging. You can expect that if, for example, let us talk about function learning instead of operator learning. If you have general continuous function to learn, and if the function change a lot very quickly, then the learning problem is very challenging and the error is out of control. And because there is no free lunch, so in general, if we have some continuous function to learn, it's difficult to get nice error bound, and we will have to make some assumptions so that the learning problem can be well controlled.
That's fair enough. Okay, Luca, let me know if you want me. Okay, Lucas says thanks. Cool. Yes, maybe I also ask just one question. So when you have this low dimensional manifold, this D0 dimensional manifold, I just wanted to know, do you assume that this is like a submanifold of the underlying like input space, or is it a submanifold of how you say your projection onto the first D dimensions? Like basically, does it lie? Does it lie in the domain of of your say decoder? Yes, yeah. If the encoder, yes, does it lie in the range of the encoder, or does it, or can it like come outside the range? Because it doesn't necessarily need to be aligned. Like I'm wondering, is it necessarily aligned with the first dx basis vectors, basically?
You're talking about the alignment, whether we have some alignment error in this.
Yeah, like maybe I give an example of what I mean. So for example, if the encoder projects onto the say we're in like L2 of the interval, and the encoder say projects onto the first Fourier like modes, suppose to have like a one-dimensional manifold that just align but orthogonal to the span of these two. Is this still within the assumption, or like does the assumption assume that the manifold is in the first two basis vectors in this example?
So originally you have some general function and you try to use Fourier transformation to project it to low frequency modes to get low dimension manifold.
Yeah, just an example of an encoder, like a concrete one,
Yeah. First of all, if you have a general function and this projection may not work quite well because some projection error, so we have to, if we want to have this low dimension manifold assumption, we have to assume that in our application, all these function U only have low frequency modes and
okay.
High frequency modes.
Okay, that's what I thought. Okay, that makes sense actually. Cool,
yeah.
cool.
All the truncation error is small.
Yeah, that's fair. Okay, cool. Honestly, it's a very interesting talk. I really enjoyed it, and I hope everyone else feels the same. Thanks a lot.